Oh, there he goes. Yes, we got it. Perfect. Thank you.
Okay, we have two submissions, but when we move to submission, yes. So my question was, is it okay if I use another type of perception? So we have to use my decision to use heartbroken. So yeah, I thought so. If just for the project goes now, okay, to be fair, I want to just like a different, not only different, like the staircase, but they are not different. They are very theoretical.
Right, folks, let's get started. Okay, we should start. Just a quick reminder, people, or just something to mention, my voice is not great today, so I might not be able to reach all the way to the back. So if you can't hear me, please move to the front. A few announcements to start off. There's a homework finally on Canvas, which is all about computational learning theory. And this one is basically all proofs, no math. So, no experiment, sorry, no code. Please get started on this ASAP because in my experience, this homework tends to take longer than most of the others because you might have to think about it a little longer or maybe not. But you know yourselves, so start as appropriately early as necessary. It's due in 2 weeks. Of course, we missed the lecture on Tuesday on machine learning and ethics. I still think this is a very important topic. It's a growing national and international priority, and it's one of those things that we should understand, try to understand as we are learning about these data-driven algorithms. I'll try to bring it back into another lecture before the end of the semester. If that's not possible, what I'm going to do is assign a video or maybe some reading as maybe extra credit. But I think it's just one of those things that is increasingly taking priority. And it's also an increasing realization that in order to reason about the fairness and accountability of data science, we need to start thinking not just as computer scientists, but we need to start talking to other people also, which is kind of a scary thought. But that's what we have. You should be hearing back about projects soon. For the exploratory projects, I'm still not done reading everything. So if you haven't heard anything from me by Saturday night, please send me a message on Canvas. I'm hoping that will be the fear of receiving 100 messages will be enough of a trigger for me to get it done maybe in a day. And there was a question about the Kaggle, the project, the competitive projects. I had mentioned in the last Thursday that you need to have submitted at least two. You need to have tried at least 2 different algorithms for before the intermediate report. And the question was, does 2 variants of the same algorithm count as different, or what is different? That's what you'd ask, right? So there are degrees of answers here. In the ideal situation, what I would hope is that you submit, say, something involving perceptron and something involving a decision tree. This will also give you an opportunity to fix your decision tree code or your perceptron code from your homework. But the question was, okay, so is the perceptron, the vanilla perceptron and the aggressive perceptron, are they counted as 2 different algorithms, or are they the same algorithm? In my mind, I think they are essentially so similar that they should be treated as the same thing. In the end, at the end of the semester, when I expect for the competitive project, I expect 6 different submissions. At the end of the semester, I'll allow maybe 1 or maybe 2 of those 6 to be variants. But for the intermediate report, I would like you to have 2 different algorithms. So essentially, since we've looked at decision trees and perceptron, basically you need to have a decision tree run and a perceptron run. It does not matter which variant of perceptron you use. And there is some element of pride in being at the top of the table, so use the best thing that you can find. Does that clarify? And yes?
And when did we have to have those to make sure we have?
Yes, so that's a good question. There was a date on the website, I forget what the date is now, if someone remembers.
The 7th of November.
The 7th of November, that's a week away. I'm almost definitely going to move it by at least a week. Yes. So, but do get started on your project, because many people came to me after the midterm worried about, the midterm grades are not optimal. No, you didn't get 100, maybe you're unhappy. So, if you think about it, the project is the place where the project counts for nearly 1/4 of your final score. And that's what will be used for grading. So please put some effort into the project, and also the project is the venue where you get to try out ideas that haven't, in some sort of a free-form fashion. So you should take advantage of that. Any questions? Okay, so if there are no questions, we're going to get back to our regular program. Today we're going to start and hopefully finish the lecture on boosting and ensembles. Before we get to that, I want to just get to a checkpoint of where we are. So over the semester, we've been looking at supervised learning. You've seen most of the slide before, but I just want to remind you of where we are. In supervised learning, we have instances. Instances could be anything in the world that needs a label. So it could be, mugs like these that have to be classified as good or defective, for example, and things like that. Instances are typically represented as features or feature vectors, and you are now experts on this idea. And concepts are these hidden functions that we don't have access to, that we want to learn. And labels are the outputs of these concepts, of these functions. Hypotheses are functions that our learning algorithm explores. Together they are called the hypothesis space. And if you want to think of learning algorithms as a black box, a learning algorithm is something that takes labeled data in the supervised learning. The learning algorithm is something that takes labeled data and produces a hypothesis, which is a function. Here it's in this picture it's h. Once learning is done, the hypothesis can now go out and label new instances in the wild. We've seen two different learning algorithms so far. We've seen decision trees and perceptron and many variants of these things. And we've encountered many different general machine learning ideas that are actually not just applicable in these contexts, but more broadly. We've looked at the idea of features as high-dimensional vectors, which is very important. We've looked at the idea of overfitting at least twice so far. And in some sense, we were asking the question, what does it mean to learn? One answer for that was online learning, or specifically the one that we saw was mistake-bound learning. Another one was in the context of batch learning or pack learning, which is, you can think of it as the theory of learning. And under pack learning, which we just concluded last week, we looked at generalization bounds. We looked at this idea of sample complexity as being important in addition to time and space complexity. We looked at agnostic learning, where the hypothesis space need not necessarily contain the concept. We looked at VC dimensions, where the hypothesis space consists of infinite functions, and the higher order bit here is that in some sense learning is the difficulty of learning depends on the difficulty on the size of the search space, either the size of the search space in terms of the number of functions or in terms of its VC dimension. Okay? So this is where we are. Any questions? Now, at the end of last Thursday's lecture, I mentioned that this theory of learning, the packed theory of learning, gave rise to some interesting research questions that were answered, and in the process of answering these questions, we got some useful industrial strength algorithms. Today we are going to look at one of them. I have made a mistake. I will have to reboot my iPad. Give me a minute. While this is happening, let me just set the stage up. We're going to look at one of these algorithms called boosting. Boosting is a specific instance of a family of learning algorithms called ensembles, or ensembling is a general strategy where you don't learn one function, you learn a committee of functions. You learn many functions that can predict this label. Once you have a committee of functions, you now need to somehow pull together the predictions of this committee to decide what the label is. This idea is called ensembling, and ensembling is extremely important. It's a very important toolkit to have in your toolkit, because in some sense, most of the instances of machine learning that we see out there, industrially, like in Google, for example, end up being ensembles of one form or another. So I plan to introduce ensembling through So I plan to introduce ensembling through this algorithm called boosting. Fine. And boosting is an example of an ensemble algorithm, or add a boost is an example of an ensemble algorithm, and then I'll introduce you to a few variants. At the end of this lecture, you should have enough tools to build what are essentially state-of-the-art classifiers for a wide variety of tasks. Let's get started.
I have a question.
Yes?
Is voting perceptron an example of ensemble?
Yes, it is. The voted perceptron is an example of an ensemble, except it's an example of an ensemble that is kind of difficult to maintain because you're keeping track of everything. Here what we'll do is most ensemble algorithms ensemble strategies have the following setup. You have a black box learning algorithm. Any black box learning algorithm, you don't care what's happening inside. It has that signature, it takes some data and creates a hypothesis. You run that a few times. You collect a few hypotheses. You don't look into the algorithm, you just run that a few times and you use the output of that. You use all the hypotheses that are produced to make a final decision, which is slightly different from what we saw in voted perceptron. So let's look at what boosting is, because this is also it turns out that this algorithm was an answer to an interesting theoretical question. So we've seen pack learning. Boosting is an idea for increasing the strength or increasing the quality of a collection of what are called weak classifiers. And I'll define formally what weak and strong classifiers are. This question was posed in a paper in the 80s, and over the few years that, very, very quickly the question was answered in the positive. So let's look at the question. Suppose you have a collection of weak classifiers. Think of it as rules of thumb. You know, these little rules of thumb that you can come up with very, very quickly. They're not going to be great, but they're going to have slightly better than chance performance. An ensemble method in general is a class of learning algorithms that compose the predictions of these rules of thumb. And boosting is something that has some strong theoretical guarantees. This is an example from slides created by Rob Shapiro, one of the creators of the AdaBoost algorithm. And the task, say, is to automatically classify what kind of a phone call you're getting. So imagine that you're running a service where people call you up and they say something, and based on what they say, you need to route that call to the appropriate place. And to give you an example of how old this algorithm is, these examples are actually from Rob Shapiro's talk. So one label could be something called a collect call. How many people know what a collect call is? An increasingly small fraction of people. It's basically when you call up someone and make the other person pay, I think. So in order to make a collect call, you can, if the person picks up and says, I'd like to place a collect call, it should be routed to the system that handles collect calls. I need to make a call but bill it to my office, that means it's a third party. I'd like to place a call on my credit card, then it has to be a different label. So this is a classification problem, right? Now, what is interesting is in this setting, rules of thumb are often correct. If the word card occurs, it's often calling card. Not always right, but you can write these kinds of rules of thumb. If MasterCard shows up, it needs to be routed to the third option. So far so good? Now, what we want to do is to make this classifier better. And one initial approach for boosting was you create a small subset of examples, this training data that you have, take a small subset, derive a rough rule of thumb. This is what we do. We look at a few examples, we come up with a rule of thumb. Oh, every time the word MasterCard shows up, I need to push it into the calling card. So you have a rule of thumb, you do this another time, you come up with another rule of thumb, you do this enough number of times, and you come up with a bunch of rules of thumb. and then you combine them all into a single prediction rule. We need to specify how to look at these subsets. I can't just randomly take subsets and hope that, well, you could. I can't, I need some way of getting subsets, and you need some way of collecting these rules of thumb, or combining these rules of thumb. And the boosting is a way of converting these rules of thumb into a single classifier. So let's formalize this. We've seen packed learning, and what we saw as the definition of packed learning in this context is any algorithm that satisfies that. In this context, we'll call it a strong packed algorithm. Essentially, a strong packed algorithm is an algorithm that comes up with the following, that has the following guarantee. For any distribution over the training data, over the instances, for any small epsilon and delta that are positive, using only a polynomial number of randomly chosen examples, the strong pack algorithm will find a hypothesis with high probability, with probability 1 minus delta. It will find a hypothesis that has a low error less than epsilon. This is basically the version of pack learning that we've seen so far. The question that came up was, what if, so first of all, notice that this is any epsilon greater than 0. The error can be any error. What if I don't have a strong pack algorithm, but I have a weak pack algorithm? A weak pack algorithm has a small error, has a large error, but less than half. So maybe, we're talking about binary classification here. So a weak pack algorithm will always produce a classifier that has error more than, say, 0.45. Let's say it's guaranteed to do that. It's not very useful. The error is high enough that it's really rough, but let's say we have a concept class for which we are able to invent a weak pack algorithm. A natural question is, does weak learnability imply strong learnability? If I have a concept class for which there is a weak pack algorithm, does this mean there exists a strong pack algorithm? Maybe I don't know what the algorithm is, but does this mean the concept class is pack learnable in the general sense? This was a question that was posed by Kearns and Valiant in 1988. Before we move on, is this question, does this make sense?
Does weak mean we're guessing above random chance?
Basically.
Okay.
Yes, weak means our classifier is better than random. And that's all we have. Yes.
If gamma is equal to 1/2, isn't it equivalent to strong?
If gamma is equal to 1/2, that's equal to strong. Yes. We are assuming that gamma is small.
Okay.
Yes. Yeah.
So it's not immediately intuitive to me why we'd have any reason to suppose that weak learnability would imply strong learnability. Can you give any intuition for why people would even ask that question? Why that would seem like a possible thing?
So first of all, you're right. I mean, it's completely, in fact, you're perfectly right. There is no reason for the answer to this question to be yes. The reason this question was posed was, it is easy to come up with rules of thumb. The question is, rules of thumb tend to be slightly better than chance. So if I have a collection, if I'm able to have a collections of rules of thumb, does this mean the concept class is learnable or not? It's a question. We don't know the answer. Maybe it's yes, maybe it's no. And that's the right way of thinking about it. There is no reason for this to be the answer for this to be yes. Maybe something is weakly learnable but not strongly learnable. Because strong learnability requires every epsilon. Weak learnability does not necessarily have to imply strong learnability. And so this is also a lesson in how the community moves forward. Someone poses this question: does weak learnability imply strong learnability? Maybe yes, maybe no. And immediately a bunch of people started working on this question, trying to prove one way or another. The question was very quickly resolved in 1 year by Rock Shapir in a paper which said, which had a provable boosting algorithm. Boosting is this idea of boosting the strength of the learning algorithm. which called the weak learner 3 times on 3 modified distributions of the data and then combined them and then repeated this a few times. Essentially, this was a proof of concept. It was not a usable thing. And then Freund improved on that by giving some optimality bounds. And then another paper which had some first experiments on real data in 92. And then in 95, Freund and Shapiro put all of this together to create this algorithm called AdaBoost, which had practical advantages over the previous methods. We won't be looking at the first 3, we'll be looking at AdaBoost. And AdaBoost came up, was followed by a whole bunch of applications and papers and useful results all around. And also along the way, it got a Godel prize for Freund and Shapiro, so it worked out well for everyone. The point here is this question was posed in, posed in 88 as to whether weak learnability implies strong learnability. And as far as we are concerned now, AdaBoost is an algorithm that constructively proves the answer is yes, okay, by saying not only does weak learnability imply strong learnability, more than that, here is an algorithm called AdaBoost that can take your weak learning algorithm and construct a strong classifier with a theorem that shows that it's correct. Okay, so we'll be looking at AdaBoost right now. Is the setting, does it make sense? So let's look at AdaBoost. Let's first look at the intuition for how AdaBoost works, and then the algorithm, and then very briefly I'll talk about why it works. In the interest of time, I'm not going to go over the proof, but the proof is available on the class website. I encourage you to go over it. So let's take this toy example here, again from Shapiro's slides. So suppose you have this class of this set of points, some of them labeled plus and some of them labeled minus. Suppose we have a weak learner that can only learn horizontal lines or vertical lines, axis parallel lines, one of these two. What we're going to do is assign a quantity that in the slides I'll call D, that is, think of it as the importance of each example. Initially, all examples are equally important. And let's say we find a classifier that classifies the data as plus and minus, by somehow minimizing the error, let's say. And of course it makes mistakes. There are 3 mistakes here and 3 out of 10 points are wrong, so the error, epsilon 1, is 0.3. Nothing shocking so far. And here's the next, the interesting thing that happens. What we'll do is we'll now move to the next round of learning. But before moving to the next round of learning, we will increase the importance. Remember that every examples come with importance, and initially all examples are equally important. When we move to the next round, we'll increase the importance of the examples where the first classifier made a mistake, and we'll decrease the importance of the examples where the first classifier did not make a mistake. So I've just shown that by changing the size of the pluses and the minuses. So these 3 pluses are now bigger. So now we have a new data set where examples are, notice, examples come with weights. Examples are weighted as to how important they are. And this is an important thing. We need our learning algorithm, the weak learner, to be able to use these weights somehow. And that's, I'm not going to talk about how to do it right now, but I want you to start thinking about how you do it, say, with decision trees or perceptrons. So let's say we have now a weighted data set, and at every round we'll maintain a set of weights called dt. dt is the set of weights at round t, which is an importance assigned to each example. It's essentially thinking about, if you want to think about this as intuitively, what it means is dt of any example is how important is that example for the tth round of learning. And let's say based on, and if you want to minimize, find a hypothesis that minimizes dt at this round, d1 in this case, let's say we find this separator that another vertical line that this time gets the 3 important points correctly, but right? Because that was we somehow try to find a classifier that correctly labels those points. But this time it makes it makes an error on 3 different classifiers, or 3 different points. And this time I'm going to argue that the error is not 3 out of 10, but 0.21. Because we need to weigh each example by how important it was while making the error. I just made up these numbers. I mean, these numbers don't have to mean anything immediately, but while computing the error, what we're going to do is compute the weighted error. Each example here, according to these calculations, has a weight of 0.7, let's say. It does not contribute an entire 1 to the error. It has a weight of only 0.7. We've made 3 times 0.7 mistakes, so the error is 0.21. More formally, the error of the classifier at any point in this round is defined this way, and let's kind of decompose this. HI is the classifier that we just learned. HI is something that says, or H in this case, is something that says what is the label for any example. It could be -1 or +1. Yi is the true label, which could also be -1 or +1. If you multiply Yi and Hi, it will be negative only if Hi and Yi don't have the same label. Right? So Yi times Hi of x, or sorry, H of x, it should be Ht, but it doesn't matter. H of Xi can be either +1 or -1. No error, it's +1. If there is an error, it's -1. Now, this example is weighted by dt of I. The ith example is weighted by dt of I. So you scale up or down the error by that quantity, and if you add up all the negatives, you get the error. And this half minus half times is basically trying to scale that by between 0 and 1. You should think about why this makes sense. Yes?
Yeah, so I was wondering that there will be like a scenario which is positive and there will be a scenario which is negative as well. So
You mean scenario or an example?
Sorry, example.
Yes.
So won't they cancel out each other?
Yes, they could. Not quite. Basically, so think about it again. So let's say, let me give you an example. Let's say you have 3 examples, A, B, and C. Let's say the error, the weight for A is 0.3. The weight, actually, by the way, this was I had a mistake here. This should not have been 0.7, and I'll tell you why that is in a minute. Let's say the weight for A is, because they should add up to 1. So let's say this is 0.5 and this is 0.2. This is dt of I for this is xi. Let's say yi, the label, the true label is +1, and -1, suppose. And this is still the training set. Let's say -1. So we've made one mistake here, right? But in some sense, the amount of error that we have made is not 1, but 0.3 in this case. So, but you wanted to consider the case where there are 2 errors, so let's introduce a new example with also, we made a mistake, one more mistake. So, h of xi times yi is, in this case, it's -1, +1, -1, +1, -1. So only the -1s tell us where the error is. Now, if I take if let's say the errors don't matter, I mean the weights don't matter, you're right, in this case it will cancel it out. So 2 pluses and 2 minuses, you add them up, you get a sum of 0. So summation here is 0, but what is the error? If the weights were all equal, what is the error here? You made 2 errors, what's the error rate, as a fraction?
Maybe 0.5 minus 0.3.
No. If the weights were all equal, it's half. Half the examples have made a mistake. Right? So even though the summation is 0, the error is 0.5 because I've made 2 mistakes out of 4. But what I really want to do is not to think of it as 2 mistakes out of 4. I have one, so the sum of d, we'll maintain the sum of d's to be all equal to 1. I have 1 unit of examples. Out of those, in 0.5 and 0.1 of the cases, I have not made a mistake. And in 0.3 and 0.1, I have made a mistake. So the error should be dt times this quantity here, which becomes 0.3, 0.5, 0.1, and 0.1. There's a minus here and minus here. And now I need to add them up. So can someone quickly tell me what's the sum of these things? It's 0.2, I think. Correct me if I'm wrong.
Yes.
0.2, yes. And now the error really is, we need to worry about, it is half minus half times 0.2, which is 0.5 minus 0.1, which is 0.4. Now the examples don't cancel each other out because the weights take care. And even if the examples did cancel each other out, this quantity will be, if they all cancel each other out, we've basically made an error every time. For every example where we made an error, we've got an example where we did not make an error, so the error is half.
So, how do we decide on detail?
We'll get to that in a minute. That's part of the algorithm. But is the mechanics of this, does it make sense? What I want you to think about is, yes?
Could you have just added 0.3 and 0.1
Sorry?
Could you have just added 0.3 and 0.1
No, I think this is just a coincidence
Okay.
in this case. I think this is just a coincidence. But what I want you to think about is why this, it's not enough to just add them up, but this half minus half, it's basically a way of taking a number between, what could have been a number between -2 to +2 and scale it to a number, push it between 0 and 1. And this is just a scaling factor. Think about it and come back after the next lecture. In order to think about it, you have to think about this, when you have x is 1 and h is -1, the product is -1. Here the product is also -1, and we weight each example. When y of x equals h of x, the product is always +1. Okay, so in this case, what we've done is we've now got an error epsilon 1, but again, we are now ready for the next round. The next round starts off in the same, before the next round starts, we need to again do the same thing. We need to reassign the weights of the examples. We need to now increase the weights of all the mistakes that were, of the examples where we just made mistakes, and decrease the weights of the examples where we did not make mistakes. So what happens is, this one gets a higher, this minus becomes bigger, this one becomes bigger, this minus we have twice now correctly predicted, so it's getting very, very small. This has shrunk a bit here, and so on. So examples get weighted up and down by whether we just made a mistake on it or not. And so now we have a new data set, a new weighted data set, and again we have to, every example comes with a weight, and now our goal is to find a classifier that has low weighted error. And let's say we find another classifier, this time it's a horizontal line, and again we find that there are mistakes. There are 2 examples where this thing has made an error, and we can now compute the weighted error again. It turns out in this case it comes up to some other number, and so on. So we have 3 classifiers now, but I'm going to stop this process and actually move to an algorithm. But is the mechanics of the algorithm, does it make sense? So you have a collection of examples, and throughout the process of learning you maintain a set of weights for each example. Initially each example is equally weighted, in other words every example is equally important. At every step what we do is we do 2 things. First, we have a weak learner, right? What we do is we call the weak learner and ask for a new classifier that has low weighted error. So we get a classifier like a rule of thumb of this kind. Then we reweight the examples based on how many errors the newly learned classifier makes, based on which examples the newly learned classifier incorrectly classifies. The intuition behind the weighting scheme is at every time step or every round, we try to make examples where we just made mistakes important and examples that we got right unimportant. So that in the next round, the learner gets to focus more on that. Yes?
So I was wondering that in this case, the W that we learned in the classifier algorithms.
The perceptron weights.
Yeah,
Yes.
perceptron weights. So how do we factor in that?
That's different. That's all inside the box called H.
Okay.
This is a different collection. So think of these weights as weights over examples. The W's that you learned are weights over features. All of that is inside this black box called H.
Okay. So my doubt was that how do we assign these different weights to these examples and still come up with a classifier?
Right. So that's a good question. So the question was, let me repeat that. I said we can take any weak learning algorithm and use it inside boosting, and suddenly now I'm asking you to use a learning algorithm that somehow knows how to weight examples. Right? How do we do that? I'm not yet going to give you the answer right now. I want you to think about it. In particular, I want you to think about how you change the decision tree learner, for example, to somehow make examples more or less important. Or if you're uncomfortable about decision tree, I want you to think about how you do that to the perceptron. There is a formal answer to that we will get to once we come to loss-driven learning, but it's just a slightly more complicated version than what you've seen. And I'll not tell you the answer right now. If you still have the question, say by the end of the lecture, come back to it. So we have three hypotheses now. In this case, we have three hypotheses. We have H1, which was this vertical line, H2 was this other vertical line, H3 was a third vertical line, was a horizontal line, and we need to somehow combine them. What AdaBoost does is it assigns a score for each hypothesis and says the final hypothesis is the weighted sum of the predictions of these things. In some sense, the way to think about it is these alphas, or every weak classifier, when a new example comes in, every weak classifier gets a vote. It gets to vote on the final label. And the alpha is the vote that it gets. A weak classifier that does well on that seems to do well should get a higher vote. The weak classifier that does not do well should get a lower vote. And the job of the boosting algorithm is to specify these alphas. So eventually what we'll do is we'll take a linear combination of these weights and then take the sign or something like that.
Excuse me?
Yes.
So for each term we will update the DI, the weights for the examples,
Right.
and also the hypothesis space for the edge.
Which edge?
The hypothesis.
We don't
space.
update the hypothesis space. The weak learner operates over the same hypothesis space.
So the edge will change after each term.
The capital H or the small h?
The small edge.
Yes. After every round, we will relearn and possibly get a new function, new classifier. Yes. That's why we have three different functions here.
So how we update the edge is not talked about here.
It's a black box. It's the learning algorithm that we will produce using the weak learner. So there is in general, the input to an ensemble method consists of a data set and a learning algorithm that we will repeatedly call and construct many hypotheses. Yes?
There is one question related to this. So if you're saying that initially our hypothesis space is the set of all vertical and horizontal lines,
Yes.
right?
Yes.
But if we're going to take a linear combination of this, we're going to get a vertical one, which is outside that hypothesis
Oh,
space.
actually, in this case, I think that might even be the next slide. No, we won't. I have a slide eventually. It turns out that for this case, the final hypothesis space is neither vertical nor horizontal. You will get something that looks like this.
Oh.
Yeah. So what boosting does is it uses your weak classifier as a hypothesis space and then produces a classifier that's not in the hypothesis space. It essentially increases the complexity. That's right. Yes.
So the sum of the alpha will equal to 1?
No, we'll see that in a minute. So we'll get to see. So in order to specify, okay, that's the. So here's an outline of AdaBoost. You're given a training set where you have instances labeled with -1 or 1, and learning proceeds in multiple rounds, and each round we make a call to the weak learner. What we do at the start of each round is we first construct a distribution over the examples. Essentially this is DT, which is asking how important is this example in this round, and then we make a call to the weak learner. The weak learner, the job of the weak learner, the guarantee that we demand from the weak learner is that it makes a small weighted error, where the weights are defined by this DT. We do this t times, we get t different classifiers, and finally we need to construct the final output, h. We need to specify two things here really, in order to make this, in order to complete the story. We need to specify how to construct this distribution dt, and we need to specify how to construct the final output. And if we do both of these things, we get the complete algorithm, subject to, modulo how we find this weak learner. That's less difficult, that's less of interest here. So I'm going to go through these two steps now. So first of all, how do you construct a distribution over these instances? We have m examples, and which means that we have m weights over the examples. So d1, d2, and so on at any round. dt of 1, dt of 2, and so on. The job of the weak learner is to try hard to correctly label examples that have high dt, high value of dt. So an example xi yi that has a high value of d should be prioritized while learning. Initially, we know nothing about these examples. So what we'll do is we'll weight them all equally. So dt of I is 1 over m. It's the uniform distribution. Let's say we have played this game for t rounds. After t rounds, what do we have? We have the previous distribution dt that was used to learn. We have the newly constructed hypothesis ht. We know the error of that hypothesis, the weighted error of that hypothesis on the training data. So these are the three things that we know. Our goal is to now construct dt plus 1 using these three things. AdaBoost specifies the following recipe, and we'll get to that in a minute, but what we want really is from dt plus 1, what we would like is examples that were incorrect in the previous round. In round t should be weighted higher. Examples that are correctly classified are less important because we have something that covers it now. So misclassified examples should be promoted. And what AdaBoost suggests is you re-weight every example by, you have a previous dt, right? For the ith example, you have dt of I. If the example was correctly classified, if yi was equal to ht of xi, then you multiply it by e power minus alpha t. I'll tell you what alpha is in a minute, but if you multiply it by e power minus alpha t, the value decreases. If the example was incorrectly classified, you multiply it by e power alpha t. And there's some normalization zt that makes sure that everything is between 0 and 1. I can put all of this together by just saying, if you know that yi and these two are all both minus 1 and 1, the product is going to be negative only if there's an error, right? So I can multiply by e power minus alpha t times yi hi. So this can, if this is negative or this is positive, this is negative, then you have error. This is positive, you have correct. And if it's correct, you want the value, the corresponding dt of I to go down. If it's incorrect, you want the dt of I to go up.
Excuse me?
Yes?
Is the alpha here the same as the previous one? How we?
It's exactly the same alpha.
Okay.
Yes. Let's stare at this a bit more. we need to specify what alpha is and what z is, and at that point, if I give you those two things, you should be able to even implement it. Z is a normalization constant. The way to get z is you first do this, compute this quantity without the z, take the sum, and the sum of the unnormalized dt's is a z. That's the easy part. Alpha is more interesting, and what Adabus says is alpha t should be the log of 1 minus epsilon by epsilon, or half of that. Now, if epsilon is a small number, let's say if epsilon is less than half, then the numerator will be more than half and the denominator will be less than half. So let's say if epsilon t is 0.75, then alpha t is half log point. Oh, what have I done? If epsilon is 0.25, my bad. 5, then it's 0.75 divided by. So this quantity is more than 1, right? So this whole thing is more than 1, so alpha is always positive. That may seem like a pointless exercise, but in the proof, when we eventually get to it, alpha needs to be positive. And also, if you think about it, the alpha will be alpha being positive is the only way in which this quantity, decreases if you multiply by e power minus alpha. Questions about just the mechanics? So far, there's nothing.
What if the hypothesis HT doesn't make any mistakes?
If HT doesn't make any mistakes,
Yes.
then what do you get? Then epsilon t will be 0. Then you can basically stop. I mean, you're not going to. You don't have to worry about it. At that point, you don't have to worry. That's almost never going to happen.
So will we discard all the calculated previous, or also add them to a final big H?
Sorry?
If there is a hypothesis HT that can perfectly do the prediction,
Right.
will we still use the weighted average of
So if HT does perfect prediction, what happens is you're essentially resetting if you work out the math, at the next time step, dt plus 1 will become uniform. Because you're saying that all examples are equal, and you'll have an infinity that you have to take the limit of. But don't worry about that, you'll never have to deal with that, because HT, I'll show you a picture, as t increases, HT keeps getting worse and worse. The error gets worse and worse. Also, alpha t is, as was observed, the vote that this particular classifier HT gets in the final prediction. Okay, so all that I have showed so far is how do you construct this distribution over examples. Notice that I am presenting a very mechanical process here. There's nothing this is a constructive proof that answered the weak learnability, strong learnability question. So I showed you how to construct a distribution. Now we need to look at the final hypothesis. How to construct the final hypothesis. What we have now at the end of t rounds is we have t weak classifiers, h1 through ht. All of them have been, so hi has been learned by minimizing the weighted error at the ith round. In addition, we have t values of alpha 1 through alpha t. Each weak classifier is, and think of it as like this noisy expert that takes an example and produces a -1 or 1. Adaboost says the final hypothesis, capital H final, is a function, right? Hypothesis is a function. It takes all these weak classifiers, takes a weighted average of their predictions, weighted by alpha, and the sign of that should be the final label. Any thoughts or comments?
My thought is that Those are some pretty heavy computations. Every example, we're doing lots of HTs.
It's not every example. This is just the final classifier.
Yeah,
This
but
is-
isn't the final classifier a compilation of a bunch of functions?
Right. Each HT is a small function. Think of HT as a rule, right?
Yeah.
Each HT is like one of those things. Like if the word MasterCard shows up, then calling card.
And thinking in complexity though, if for each example you're essentially running, say, 20 functions over it to
Sure.
get the solution.
Yeah, but it's much cheaper. I see a point. If each small HT is computationally expensive, then the whole thing is going to be very expensive. That's your point, right?
Yes.
Yes. And
It's usually not a problem.
it's usually not a problem.
Okay.
Yeah, surprisingly that never comes up. So it doesn't matter. Do you have a question?
So, I was wondering that this will be prone to overfitting.
Hold on to that thought and I'll show you some theory that there is result that shows this can be prone to overfitting, but in practice it's not, which is kind of a strange result, but I can point you to some papers that shows that it tries to explain why. But yes, it can be prone to overfitting. So let me just show you the full algorithm. We are given a training set x, xi, yi. Yi's are -1s or 1s, and our goal is to learn this strong classifier. The hyperparameter, in addition to any hyperparameters you may have had for the weak learner, we have one more now, which is t, the number of rounds that this game has to go for. You initialize d1 of I to be uniform, which is just 1 over m, and you proceed for t rounds. At every round, first you find the weighted, so you find a hi that has low weighted classification error. In fact, the theory does not even require that it should have a low weighted classification error. All it requires is that the weighted classification error should be better than chance. The error should be less than half. That is all that is needed for the theory to work. And then, once you found the classifier, you compute the vote that this classifier gets in the final hypothesis, which is this alpha t. Once you have the vote, once you have alpha t, you reweight the examples. Now you say this hypothesis has now taken care of these examples and it's not misclassifying. Here, let me now target the weak learner towards this other set of examples where we seem to be making mistakes. So you reweight the examples, so you get dt plus 1 of I, and you're done. You loop back. Once this runs for t steps, you have t classifiers and t alphas, you put them all together and you return a final hypothesis, which is the sign of these. It's a function. The function is, it takes, given any new example in the future, it will compute the sign of, it will run all these t weak classifiers, get t predictions, take the weighted sum of those things, and then take the sign of that. And just to give you a pictorial example, you have 3 weak classifiers. Each of them comes with an alpha, and we need a sign of these things. Eventually, it turns out in this picture, the final decision boundary is not in the hypothesis space that we were working on at all. It's a different hypothesis, which in some sense we have increased the expressiveness of our classifiers by doing this process. And this is not quite right, there should be a sign here. Yes?
Are there cases where weak learnability under a different hypothesis space implies strong learnability under the original hypothesis space?
Can you give me an example?
Like, for example, let's say you're really good at, like, you have weak learnability with linear classification, and then, like, quadratic classification, everything is your strong one. If you have,
Oh, I see. So, the definition of, you're changing the definition of strong learnability.
I'm just saying they're different hypothesis spaces for each.
So, that's exactly what's happening here.
Yeah.
In fact, this is what's happening. Weak learnability and each weak classifier, the little h's, are operating in a different hypothesis space from the big H. So, boosting is an example where weak learnability in hypothesis space 1, the vertical or horizontal line, implies strong learnability in a different hypothesis space. It's strong learnability of the concept using a different hypothesis space. The concept remains the same. There's a fixed concept and we are trying to learn it either using just vertical and horizontal lines or using something else. What boosting seems to be doing is it incrementally constructs a new hypothesis space. Because if I added a new line, it might have, if I had another line, it might have added another step here.
Is it correct to say then we will always perfectly classify our training set?
Yes. In fact, that's what happens, and that might be one of the slides that's coming up. Yes.
So for each HT, is it the best classifier it can be? Like it has to search over all of hypothesis space to find.
The theory does not require it to be the best. The theorem that we'll see maybe in the next slide is it requires each HI to have a weighted error better than chance.
Better than half?
Yes, less than half error.
Error.
Yeah. That's all it requires.
So it says as soon as it finds an error less than half,
You can stop. But in practice, if you're going to do that, might as well just find the best one, best weighted classifier. Yes, you first and then you. Yeah.
Following on our question from a little bit ago, if epsilon was 0 for one of these rounds, we would be computing alpha equals 1 minus epsilon over epsilon, right? So divide by 0.
Which means
so we have an infinite alpha that would dominate all the others, we would just use that classifier.
That's exactly right. It simply says and that's right. If epsilon is 0, what you get is alpha is infinity, which simply says this classifier was perfect, just use this. Everything else can be thrown out. Yep. You had a question, yes.
So we don't need the sum of the weights to be 1?
Which weights? The
The
alphas?
weights of each example.
We do need the sum of the weights to be 1, and that's why here the denominator ZT is the normalizer that makes sure that the sum of the weights is 1.
Okay. It's just not that obvious to me.
Yeah, so that's right. In fact, so let me just here. So ZT is a normalization constant that the way to compute that is you first compute the unnormalized weights, add them up, and that's your Z.
Okay.
Was there a question at the back? Okay. So all I have shown you is, this procedure that does something with data. Why should it be a good thing? I mean, in general, if you just see an algorithm or this kind of a function that does something, why should you believe it? In order to believe it, you need a theorem. And thankfully, AdaBoost comes with a theorem, and it looks like this. Suppose you run, and this is just a caricature of the full theorem. You should look it up if you're interested. The training error behaves in the following way with AdaBoost. Suppose you run AdaBoost for t rounds. If you run it for t rounds, you get t weak classifiers and t errors and t alphas. Suppose every error behaves this way. Every epsilon t is equal to half minus some gamma t. And all the gamma t's are more than some gamma, which is more than 0. Basically, this is saying all the epsilon t's are less than half. Then, the training error of the final classifier, the one that we construct, is going to be less than e power minus 2 gamma square t. The interesting part here is the e power minus t. So, as t increases, the training error exponentially decreases. The training error of the final classifier exponentially decreases. As not the epsilons. I'm talking as t increases, we don't care about the epsilon increasing or decreasing, but the training error of the final classifier exponentially goes down. And the proof for this is actually rather simple. But let me just walk through what this means. Basically, this says if you have a weak learner, meaning the epsilon is less than half, as the number of rounds of boosting goes up, the training error decreases. And as I said, the proof is rather simple. It's so simple that you should be able to work it out yourself. In fact, I insist that you should go through the proof on the class website, because it will kind of show you how all the alphas and the epsilons and the d's were carefully constructed so that this theorem could be proved. It's an example of a very neatly done piece of work. One question that I think some of you kind of hinted: is it enough to bound the training error? Sure, the training error goes down exponentially, but is that enough? What do you think? Yeah.
So one case could be of overfitting, like if you overfit, the training error will be very low.
Yes, that's exactly right.
Generalization error could be high.
So it's not enough to say that the training error is 0, right? Training error being 0 could imply there's overfitting happening. But on the other hand, if, in the last lecture that I was here on last Thursday, we had this agnostic learning theorem that said the generalization error is less than the training error plus some VC term and epsilon and delta term, right? If the training error goes down, the right hand side, we have a bound on how bad the test error could be. The problem, so what's going on here? Is it enough to push the training error to 0, or should we do more? Think about this question. It turns out that boosting also changes the VC dimension, because as the number of rounds increases, you're changing the hypothesis space of H, capital H. So VC increases, but the training error goes down, so both of these things kind of interact with each other. Empirically, what happens though, on multiple data sets, as the number of iterations increases, training error rapidly drops down to 0. This is a typical picture of the training error of the capital H final. As the number of rounds increases, it rapidly drops down to 0. Also, empirically, another interesting thing, this kind of goes back to the point that came up earlier, the epsilon t's tend to increase. As we go along, as the number of rounds increases, the errors of the individual classifiers tend to get worse. So the weak classifiers get worse and worse as the number of rounds increase, but the training error goes down to 0. Yeah?
What are those the unweighted errors?
Epsilon t?
Yeah.
I think there's a weighted errors. I have to think about this, but
It says weighted error on the left of the graph.
yes, there you go. Yes, so that must be weighted errors.
Intuitively, it seems like that would be why it goes up, because those examples are harder and harder to classify.
They might be
the ones
hard.
that we keep making mistakes on.
That's one thing. Those examples might be harder and harder, or they might just be nice. So we are trying to now struggling hard to fit the noise, and we are not doing it successfully. Yes.
Isn't epsilon the generalization error?
No. Here epsilon t is the error that we defined. It's the error of the weighted training error of the after the tth round.
Because I thought we got it from the back learning module.
No. This is a different epsilon. This is a different epsilon. There seems to be a big. I've never seen this graph being so vociferously discussed. What's going on? All good? Okay. Yes.
I'm curious if you have, or what the graph looks like when you don't do weighted error.
I don't know. I have to try it, or you should try it. I suspect what will happen is it will also go down. Oh yeah, it is, because let's see. Try it out. I mean, I don't want to spend too much time on that, but I think it will go down. But the real thing that we care about is test error, right? And what learning theory tells us is, the training error will keep decreasing, but as learning goes on, the edge final becomes increasingly more complex, because in that picture that we had, we are adding more and more fine-grained things. We are essentially drawing little circles around each positive example and saying this region is positive. So it becomes more and more complex, and we know from learning theory that as complexity increases, the generalization error gets worse. So what we expect is training error should exponentially go down like this curve here, but generalization error goes down and then goes up. Should go down and go up. The bottom curve, the training error, is from the Agnostic theorem. The other one is what we expect from learning theory. Empirically, however, this is a bit of a surprising result. Empirically, what happens, what seems to be happening across multiple data sets, is that the training error goes down to 0, and the test error generally seems to stabilize. It does not seem to go up. And in fact, it even slightly decreases a bit even after training error hits 0. It's a bit of a strange observation, test error decreasing even after training error hits 0, and there have been multiple possible explanations for this. There's one very cool explanation from this paper by Freund and Shapiro and Bartlett and Lee, which has an interesting explanation that has to do with this idea of margins and things like that. You should check it out. But let me just quickly summarize AdaBoost. The nice thing about AdaBoost is we have only one additional hyperparameter to tune, the t, the number of rounds that this has to go on for. It can use any weak classifier subject to that question that I have not yet answered on how do you find the classifier that has weak weighted error. And I'm not going to answer that question today. Think about how you would adapt the existing learning algorithms to do that. And when we get to learning with loss minimization, there will become like a general purpose strategy for building these kinds of weighted, cost-sensitive classifiers, essentially. But the caveat is that, it typically depends, the quality of AdaBoost depends on the data set. It's not clear upfront. I cannot give you a guarantee that AdaBoost will always be better. It depends on the choice of the weak learner. It turns out that if your weak learners are too weak, it takes many iterations to get a good classifier that's underfitting. If your weak learners are too strong, then it tends to, or too complex, it leads to overfitting quite a bit. But one empirical thing that happened, I think in the mid-2000s, is from Rich Caruana's group, is this observation that if you have boosted decision stumps, you know decision stumps, right? And you know boosting. Now you can build boosted decision stumps. Boosted decision stumps tend to outperform many classifiers when you have small feature sets, like about 300 or so dimensional problems. Boosted decision stumps tends to be the best general purpose classifier as of 2006. We are a decade past that, so things might have changed a bit, but I know for a fact that in a lot of industrial applications, people tend to use these kinds of ensemble methods if they want to get good classifiers without thinking too hard. One exercise for you is now think about how you might implement a boosted decision stump. For that, you need to now think about how you would implement ID3 to minimize weighted error for every example. And for that, you need to start thinking about how the entropy calculations change. Alright, so let me now generalize this discussion beyond AdaBoost to general ensemble methods. In general, ensembles are meta algorithms that take a learning algorithm as input and combine the outputs of multiple classifiers. They tend to be empirically robust. About a decade back, there was the $1 million Netflix challenge. Have people heard about the Netflix challenge? An increasingly small number of people. It was this $1 million machine learning challenge where Netflix gave data for, about movies and people and how people like movies. And the task was, if a person likes this and this movie, what will be their rating for this other movie? That was the classification task. That was the prediction problem, and it was a pretty cool community challenge that kept a lot of people occupied for a while. It turned out at the end of like a year or so that they gave, the team that won was actually an ensemble. They used an ensemble. In fact, the team itself was an ensemble because two different teams that had been doing well combined, they literally just stacked their two classifiers that they produced and got a better result. And the name of the team was also the ensembles. So it turns out that this strategy tends to be rather robust. Boosting is an example of an ensemble method where there is the initialization process where all training examples are weighted equally. You iterate multiple times, and at each round you train a model on the weighted data set. You compute the error, and then you reweight the data, and you do this like hundreds of thousands of times, and you return the final model. That's the weighted classifier. This is just an example. And just to one final thing to say about boosting. Boosting has been studied because it's theoretically so easy to understand. Not easy, but theoretically it's somewhat easier to analyze. So there was a paper from the couple of papers that mentioned how boosting, add a boost, is a maximum margin method. You can think of boosting as a variant of a logistic regression kind of a model. There are multiple different perspectives on boosting. It has been theoretically well studied. There have been multiple PhDs around this strategy of algorithms. So if you like this kind of stuff, I encourage you to go read more about this because it's one of those things that's both empirically useful and also theoretically easy to, or theoretically nice. Another ensemble algorithm is called bagging. Bagging is short for bootstrap aggregating, and it's a rather simple algorithm. Literally, this is the only slide I'm going to have about bagging. You have a training set, m examples, you repeat m times. What you do at each step is you subsample the data with replacement, you create a new data set with a different m prime set of a number of examples. So you have a new data set, but this data set is sampled with replacement, which means you have a bag of examples or you have a bucket of examples. You take one out, you put it into this thing, put the example back, you take it out again, and so on. You know what a sampling with replacement is, right? So you have a new data set, and now you train your classifier, any classifier, your decision tree. You can train a logistic regression, a 15-layer neural network, decision stump, whatever you want. You do this m times, so you get m classifiers. At the end, your final classifier is a voted version of these individual classifiers. So you get CIs, I should have used HI. At the end, when you want to make a final prediction, after training is done, you just call all these m classifiers, ask them all to make a prediction, each of them gets a vote. This is bagging. It comes with, the lineage of bagging is from the statistics literature, and it comes with some nice statistical guarantees. And notice that already you have one more learning algorithm in your mix, right? This is a meta algorithm that you can put on top of anything you want. Oh, looks like I have two slides for bagging. I like. You can think of bagging as averaging over. If you are doing regression, your combination is just averaging over the underlying regressors. If you are doing classification, you can think of it as voting. This is kind of obvious, so no reason to think about it. These multiple subsamples of data that are you collected to create the training sets, to create a training set at the ith step, they are called Bootstrap Replicas, which is basically samples with replacement. Not repetition, replacement. And that's why it's called bootstrap aggregating. And it turns out that bagging seems to work surprisingly well on many real tasks. And it's so easy to implement. You have a learning algorithm. You already have decision trees, right? Or perceptron. Now you can do bagged decision trees. It turns out that one observation that has been made is if changing the data set slightly makes your classifier, changes the classifier, then bagging tends to be robust over these kinds of perturbations. So it's robust to instability in the data. An example of back decision tree is, you create T bootstrap samples. If I want, you pick a number T or M if you want number of examples. You create those many bootstrap samples. You train a tree, and in this case, I'm showing an example of a regression tree, something that we did not cover, but they exist. You should be aware of it. When at the final prediction, what you do is you have all these trees. Each one of them is going to make a prediction. So this tree predicts 0.23, and let's say this one predicts 0.31. You take the average, and the average is the final prediction. That's the idea of bagging with regression, for example. An interesting variant of this, and that's probably the last thing I'll do today, is called random forests. How many people have heard of random forests? A non-trivial number. Random forests are a variant where, in addition, you do this, you start off by, in a way that looks exactly like bagging, you draw a bootstrap replicate, a bootstrap sample of the data. In addition, you also subsample the features. At any round, you only use a subset of the features to build a classifier. That's it. And the classifier that you build is not any classifier, but it's a decision tree. So you draw a subsample of the data with replacement. You draw a subsample of the features, build a decision tree. Keep the tree, do this process again. Do this thousands of times. You get thousands of trees, and your final prediction is going to be the average or the voted prediction of these trees. This is called random forest. So just to wrap up this discussion on boosting and ensemble, ensembling is an important idea. It's one of these tools that keeps coming up all the time. It tends to give robust classifiers. We looked at one example of ensembling in detail, namely boosting, in particular the algorithm called AdaBoost. AdaBoost has an interesting lineage from theoretical perspective. It started off as a question about whether weak learnability implies strong learnability, and AdaBoost is a constructive proof for that, for the fact that the answer is yes. You should know what the algorithm is. You should think about how to implement this algorithm and how you do this, how you use any learning algorithm to minimize weighted accuracy or weighted error. In general, boosting belongs to this family of algorithms called ensembles. There are other ensembling algorithms. Bagging and random forests are the ones that are most popular. You should be able to implement bagging and random forests today, because it's just one extra outer loop over an algorithm that you've already implemented. So since the question of projects and Kaggle came up earlier at the beginning, and I said you can make 2 submissions. Bagging is a different submission, for example. Random forest is a different submission, and boosting is a different submission. So now you can implement 5, but boosting or bagging with decision tree is different from bagging with perceptron. So now you have many learning algorithms that you can implement. Alright, let's stop now, and I'll see you all on Tuesday. Please take a look at the homework, start working on it, because it's going to take time. Subsample the features. If you have 100 features, you only take like 10 of them. I don't know, like, yeah.